Like I said in the email that I sent out earlier, we're running just a little bit behind schedule. We're going to try to play catch-up today by getting through two major concepts dealing with the Bernoulli equation. All right, so what we'd like to get done, first, right, finish our derivation of the famous Bernoulli equation, BEQ along a streamline. Okay. As well as learn how you apply the Bernoulli equation between 2 points in a steady flow. And third is derive and apply the Bernoulli equation across streamlines. Okay, so we'll see, right, that basically all we're doing today is a couple different forms of Newton's second law, right? F equals ma. So in the last lecture on Wednesday of last week, okay, as a little review, we introduced this idea of, or these two ideas, what we call Lagrangian and Eulerian representations of the world, right? And we said we've got this Eulerian representation of flow that can be described by streamlines, which are lines that are tangent everywhere to the velocity of a fluid. Okay, by that definition, there's no such thing as flow across streamlines. So we said, all right, so we've got this idea of a streamline. We're going to set up some, what we call a streamwise coordinate system. Let me make this blue, because, all right, where the streamwise coordinate system at a point is defined by unit vectors s and n, okay, basically a tangent and a normal. And the distance along the streamline is defined by s of t. And then the curvature of the streamline at a given point is defined by its local radius of curvature, which we called script r. Okay. And so we said the velocity in our new Sn coordinate system, okay, was written v equal to v sub s, right, the s direction, plus 0 normal. Okay, this is basically expressing that the velocity is directed tangent to the streamline. Okay, there's no component that's crossing the streamline because that would violate the definition. And we said then that this could be written as ds dt plus 0n. Okay, so the rate at which the distance from the origin of our streamline is growing, okay, directly along the streamline, and then that the acceleration of a particle moving along the streamline could be written as a equal to as, the s direction, plus an in the normal direction, where as is equal to v times dv ds, and an is equal to v squared over r. Okay. Now, these accelerations are written as Lagrangian accelerations, meaning, and I explained this before, our flow can be completely steady in an Eulerian sense, meaning that any fixed position in space, the velocity there, the speed, nothing is changing with time. But we can have the velocity can be different at different points along the streamline. And so this streamwise acceleration is reflecting the acceleration of a particle, if we were to track that particle, okay, Lagrangian representation, if we were to track that particle as it moves through these regions of different speeds. So that gives us our streamwise acceleration. And then our normal acceleration is simply the radial acceleration necessary to bend our particle around some locally circular section of curvature. Okay. So these are the two pieces that are going to go into our expression of F equals ma. Okay? Or namely, these are the two accelerations that we're going to be plugging into our Newton's second law. And so Bernoulli's equation, for all of its sort of mystique, is really just about understanding where the forces come from and then plugging them into the left-hand side opposite each of these two. So we're going to sum up the forces that push and pull a particle along the streamwise direction, okay, and put them opposite this streamwise acceleration, and then the forces that are acting across the streamline opposite this normal acceleration term. And we'll get the two important versions of the Bernoulli equation. So, we've got two important assumptions here. And I think this is about where we left off last time. First is that the flow has negligible viscosity. Which means there's zero shear stress. Okay? No friction is occurring. And the second, is that the flow is Eulerian steady. Okay? Which means, again, that if you were to place some sort of probe into a point in the flow and monitor it over a period of time, nothing changes at a fixed point. So we've got our F equals m a, and if we don't have friction, okay, or shear stresses acting, then really what goes into the left-hand side here for our forces can only be caused by two things. One is the weight of a fluid particle, okay, the fluid's own weight, what we call a body force, and the second is going to be pressure. Okay, so this is a body force, and then the pressure is a surface force because it acts on the surface of a parcel of fluid. M, pretty self-explanatory. Got a parcel of fluid, it's got some mass, and then for the acceleration, okay, we're going to have the a sub s and the a sub n, okay, forming our two acceleration directions. So the way we're going to approach this now is through essentially a free body diagram. Let me drag in my sketch. There we go. Quick question. This is going to hinge on us being comfortable with an element from calculus. Taylor series approximations. This is something that rings a bell for you guys. I guess show of hands if you have worked with Taylor series approximations. Good. All right. So I don't need to go too in depth on this, but basically the idea is, if you know a quantity, let's say you've got something that you're trying to estimate. We'll call this f of x. Okay. And you only know information about this function at one particular point in space, and you want to estimate this function's value at some nearby point. The idea is, if this is x naught, we'll call this distance, delta x. Then you can basically say that f of x naught plus delta x is approximately equal to f at x naught, a value you know, plus df dx times delta x. Basically, this value plus a linear slope approximation passing through that point times the distance away. Okay, that's a first-order Taylor series approximation. And a lot of the stuff we do in this class is going to be based on this sort of first order approximation of the way that things like pressures and shear stresses change. So, we'll call this first order TS. Okay, so we've got this this fluid particle. Okay, it's this sort of rectangular prism that is moving along a streamline. Let's go ahead and draw in a coordinate system. Okay, so we've got our streamwise coordinate, our normal coordinate. We'll say that this has side lengths of delta S, okay, in this direction, delta N in this direction, and we'll go ahead and say it's say delta Y across, okay. Now, I'm going to, over here on the side, I'm going to go ahead and draw in, we've got our X and our Y coordinate system, oh sorry, X, Z, Y, and we've got our S and N coordinate system. So basically our SN coordinate system is just rotated up through some angle we'll call theta. All right, so what forces we have acting on this? We already said that in an absence of viscous shear stresses, we've got weight to worry about, and we've got pressures to worry about. In this case, we're only going to start off by summing things up along the streamline, okay, in the streamwise coordinate. So we've got, oh come on, I want that to be green. We've got the weight of the fluid element. And then we've got, right, we're going to have some pressure acting on this face and some pressure acting on this face. If we assume that at the center of this particle here, we can call the pressure here P naught, okay, then we can evaluate or estimate the pressures on each of these two faces using a first order Taylor series approximation. And it's going to look like P naught minus dP ds times delta S over 2. Okay? And then it's acting over a face with an area of, here, let me move this so I'm not crowding things. It's acting over a face here that has an area of delta Y, delta N. Over here, we've got P naught plus dP ds times delta S over 2, all acting over an area of delta Y, delta N. So, schematically at least, we've got all of the forces we're concerned with at least drawn in at this point. So let's go ahead and write out a little bit more explicitly weight, pressure. What each of these look like. So for the weight, right, we know we could do this using sort of classic statics approximations, where we've got the total weight, we've got the weight, normal axis, and weight along the streamwise direction, where this triangle has an angle theta that is the same as, right, the inclination of our streamline. And so we'll find that, right, that Ws, that is the component of the weight acting along the streamline here, is equal to rho times g times, equal to rho g delta S, delta N, delta Y. Okay, that's simply the volume of this rectangular prism times sine of theta. And then likewise, we can write Wn here is rho g delta S, delta N, delta Y cosine theta. Okay. The pressure, okay, the force due to pressure here is going to be written as P minus dp ds delta s over 2 and delta y minus, okay, p plus dp ds times delta s over 2 delta n delta y. Okay, all I'm doing is this force minus this force. And what we're going to get here is negative dp ds times delta s delta n delta y. So, summing up the forces along the streamline, okay, so F sub s equal to, right, m times a sub s. We can write this now as negative dp ds times delta s delta y delta n minus rho g delta s delta y delta n cosine of theta is equal to, right, the mass can be written simply as rho delta s delta y delta n times, okay, acceleration in the streamwise direction. And now, note we've got this this trio of terms, okay, that gives us the little elemental volume. We could think of this as being delta V, which is the volume of our little our prism. We've got it present in all of our entries here, so we can just cancel it out, and we end up with an expression that says, blank, a sub s is equal to, or rather, rho a sub s is equal to negative dp ds minus rho g sine theta. And I want you guys to write this down because this is an important result that allows you now to link accelerations of fluid particles to pressure gradients and gravity. But just so that it doesn't seem like this got magicked out of nowhere, remember, all this is F equals ma, where we've got now, right, basically m times a sub s is equal to, right, the surface forces, let's call this F surface plus F body, okay? But it's all been divided by per unit volume. All right, so if you multiply this by some volume, you get what it looks like F equals ma. It's just Newton's second law. So now, one last step to turn this into the Bernoulli equation. We've got to recall, right, that a sub s can be written as, right, v times dv. Turn off that. dv ds. So this turns into rho v dv ds is equal to negative dp ds minus rho g sine of theta. We want to do something about this sine of theta. What we're trying to do is get everything expressed as some derivative with respect to s. Okay? Because once everything is a derivative on s, we can integrate on s, and we simplify our equation further. But this sine theta term, I want to inspect what this actually looks like, right? So here's delta s, okay, delta z, and call this delta x. So for a streamline inclined to some angle theta, we can say that sine theta is equal to, right, delta z, delta s, which is approximately, as those deltas get very small, turns into the derivative of z. on S. So rho v dv ds is equal to negative d rho ds minus rho g dz ds. Okay, we are almost there. Okay. So there are some additional identities that allow us to turn these partial derivatives into total derivatives. We're not going to worry about those for right now. Starting to get a bit more involved. But and there's one more identity that says that v dv ds can be written as d ds of v squared. Oops. That's supposed to be d ds of v squared over 2. And so our second to last way of expressing this then is rho dds of v squared over 2 plus dp ds plus rho g dz ds is equal to 0. Okay. Again, we're still working with f equals ma. It's just that now we've got a minus f, or the ma minus f is equal to 0. And now what we're going to do is just integrate on s, okay? Because everything in here involves a derivative with respect to s. So integrating with respect to s here, and assuming that rho is constant, we get 1/2 rho v squared plus p plus rho gz, okay, is equal to a constant. All right. And this right here is the famous Bernoulli equation. Now, at first blush, this doesn't look like it's that. It's right. We went through a bunch of manipulations. We integrated, but what is it actually telling us? Essentially, what we've done is, since we start out with f equals ma, okay, based on Newton's second law, and then we integrated it over a distance, we've got an expression of conservation of energy here. And the beauty is that this number, we don't actually care what the value of this constant is. That's pretty meaningless. All right. What's important is that this constant remains the same at any 2 points along a single streamline. So if you happen to know what the velocity and the pressure and the elevation is at one point along a streamline, and you only know 2 of those other quantities at a different point, then you can solve for the third. There are a few important assumptions that we need to keep in mind. We'll do an example in just a second. But the Bernoulli equation is one of the most widely used and absolutely the most widely abused equations in fluids. Okay? You guys are going to mangle this beyond recognition at some point, each and every one of you. Okay? So it's my job to try to help you understand, at least ahead of time, so when you're going back and sort of forensically figuring out what went wrong in an application of Bernoulli, what the restrictions are on this. Bernoulli equation limitations. Okay, these are can be thought of as the inviolable laws of the Bernoulli equation. It only applies in steady flow. Okay, that is in an Eulerian sense. No viscous shear stresses. Cannot be applied across streamlines at least not yet. There's a different form that we'll use in a second to do that. And it assumes incompressible homogeneous flow. That is, it assumes that the density is constant throughout. Okay. So if you stick to these assumptions, then you will be safe in using the Bernoulli equation. So let's see how it's applied. So for example, say we've got a there we go. Say we've got a tank that is partially filled with water. Okay, so it's filled with water, but it's also pressurized with air at 150 kPa, okay, gauge pressure. And then the bottom of this tank has an exit pipe that goes through a reducing valve, and exits to the atmosphere here. We'll say that there's a 5-meter elevation difference between the top of the water in this tank and where it exits through this jet. Okay, we're told this is water. I think that is all that I need given. So to summarize the given information here. We're going to go ahead and, before we write down our givens, there's one step we can take to make this problem a little bit more organized. Okay, this is always what I tell people to do, is draw out your system that you're applying the Bernoulli equation in, and place points, okay, that you're sure you can apply Bernoulli between. What I mean by that is, let's say we know something about the fluid. Okay, up here at the very top of the tank, we know the pressure, okay? We know its elevation above some datum. And if we assume it's a pretty big tank, okay, this is an assumption that we see a lot, is if we assume it's a large tank, then we can assume that the velocity here is equal to 0. Okay, so we know some information about the flow at this point. So we're going to go ahead and make that a point in our flow. We'll call that point 0. Now, if we go from point 0 down to this point where it's in line with the exit, but it's not, hasn't yet turned to this corner. We could say, all right, between these 2 points, have we violated any of these assumptions? All right, the flow is steady. Sure, we'll go ahead and you'll be told. You're safe to assume flow is steady in every problem you're given in this class, unless you're told otherwise. All right? So we'll assume the flow is steady. We're going to assume that it's inviscid. Are we crossing any streamlines? Well, not necessarily. It is basically, it's safe to assume that a fluid element that starts here at the top is eventually going to find its way out through the exit of the system, right? So some streamline is going to connect those two. And then between these 2 points, is the fluid density constant? Well, yes, it is. So this is a valid point. We could call this point 1. And then the final point is where we're trying to solve for something. Okay, it's the exit of the system. And once again, if we can say that these 4 assumptions are satisfied between points 1 and the exit, we can label this exit point number 2. So we've got 3 points in our system. So we know that, right, P naught is equal to 150 kPa we know that z naught here is equal to 5 meters. And we can say 5 meters here because actually it doesn't matter where you call z equals 0. So for convenience, we're going to go ahead and say that z equals 0 passes right through the center line of this exit pipe, so z is measured upward from there. And we know that v naught here is equal to 0 because we're assuming a large tank. And what we're asked to find is the velocity at the pipe exit. Okay. So we solve problems like this. The reason that we draw these points here is because it allows us to solve it in steps. Okay, and so we're going to solve it this way, and then I'm going to show you that essentially we could drop this point 1 entirely and solve directly from 0 to 2. Okay, and we'd get the same solution. But you can never draw too many points, but you can draw too few. So for homeworks and for exams, if you're not sure whether you can leave a point out, for example, if you think you might need to solve for a velocity somewhere that it's not given, go ahead and put a point there. Okay? The worst you're going to do is spend an extra 2 lines solving for a quantity where you don't necessarily need it, but it's not going to give you an incorrect solution. So solution step 1 is going to be apply the Bernoulli equation between 0 and 1. So it's going to look like P naught plus 1/2 rho V naught squared plus rho G Z naught is equal to, right, a constant. But because this constant is the same for both of these points, we can say that's equal then to P1 plus 1/2 rho V1 squared plus rho G Z1. So we can get rid of this constant entirely. We don't care what it is. What we care about is the fact that the sum of these 3 quantities is the same at those 2 points. So from here, we can say, all right, from our givens, right, we know what P naught is, we know what V naught is, and we know what Z naught is. Right? At this same point, we know what Z1 is, okay, because it's just a 5-meter change in elevation. And then here, because this is a essentially because this is still in sort of the main body of the tank, right? We can assume that V1 is still 0. Okay. So we only have one unknown, and that's P1. And so we could say, right, P1 is then equal to P naught plus 1/2 rho V naught squared plus rho G Z naught minus 1/2 rho V1 squared minus rho G Z1. And because we know that these are both equal to 0, we end up with P1 equal to P naught plus rho G Z naught minus Z1. It's just hydrostatics. Right? So there's a fun trick. The Bernoulli equation reduces to hydrostatics when you don't have motion. Good to know. So before we go any further, or rather before we solve for this and actually get a numerical value, we're going to now apply the Bernoulli equation between 1 and 2. We've got P1 plus 1/2 rho V1 squared plus rho GZ1 is equal to P2 plus 1/2 rho V2 squared plus rho GZ2. So let's write in some values here, right? We know that this is equal to 0. Z1 is also equal to 0. Z2 is equal to 0, right? Because they're both along that line that we've defined as z equals 0. And P2, okay? Oh, come on. Here we go. We didn't say anything about P2 yet, right? The pressure at this point. Here's another piece of important information for when you're solving problems involving the Bernoulli equation, is that the pressure inside of a what we call a free jet, okay, is always equal to the ambient pressure around it, the ambient surrounding pressure. So in this case, that means that the pressure at point 2 is equal to atmospheric pressure. Or since we're working a gauge, we can say, oops, P2 equal to 0, right, gauge pressure. And since we know P1 as being P naught plus rho g z naught minus z1, we only have one unknown, and that's V2. So finally, we could plug all of this in for V2, right, squared would be P naught plus rho g z naught minus z1 times 2 over rho be the root. V2 would be the root of that quantity, and so I'll go ahead and write this in. This is going to be, right, P naught is 0 pascals gauge plus, if we're dealing with water, rho g is 9810 Newton per cubic meter times a 5 meter change in elevation times 2 over 1,000 kilograms per cubic meter, and we should get about 19.95 meters per second. Okay, so we are going to have to do, we've got one more day with Bernoulli, so we can wrap up the application across streamlines on Wednesday. But the takeaways from this, yeah? Sorry, what? Yeah. Oh, you're right. I'm sorry. Yes. That should be 150 kPa. Sorry, that was a typo, or I wrote this incorrectly. This answer should still be correct. Okay. So I will see you guys on Wednesday. This is a good section of the book to read. We're trying to get through it quickly, so if you're having trouble understanding it, definitely consult chapter 3.